Biochem test review. Just going to blow through it. It's going to be great. Go get some lunch. All right, chapter 1, biochemistry. Need to know, probably not too importantly, but if you don't know the structures of the cell, all the different organelles, know them. I should have gone over those in cells and tissues. Need to know which ones are the net charges on these different parts of the atom. So the protons, positive, neutrons, neutral, alliteration, and that leaves you with electrons are negative. And we have our electron shells. So this pretty much the electrons circle around the nucleus that has the neutrons and protons. And our first shell has 2 atoms, and then every successive shell has 8 atoms in it after that. And the last shell is called our valence shell, and that's the one that all the different electron transfers take place in. So that's our valence shell. You know that's the outermost shell, and those are the ones that participate. First one has 2. All successive ones have 8. All right, different types of bonding. Definitely need to know these for the exam. For our ionic bonds, this is when bonds are formed with the attraction of positive and negative charges. So what happens is sodium, in this example, we have salt. So sodium loses an electron. So if it loses a negative charge, it becomes positive. That's why it has a positive on it. The chloride accepts that electron, thus filling its valence shell and becoming negative, and that positive negative opposites attracting is what makes the bond. This is very weak in a polar solvent such as water, so it dissociates. Covalent bonding, this is when atoms share electrons, so they kind of combine all their money to make a bond per se. There are 2 different types. There are nonpolar and polar. Nonpolar is when they share them equally, such as H2 or O2, whereas polar, the electrons are shared unequally. So oxygen they kind of hoard them a little bit closer to the oxygen molecule, thus creating a partial negative, a little bit further away from the hydrogens, thus creating a partial positive. So that is a polar versus a nonpolar. Coordinate covalent is just when one atom supplies all the electrons. So in this case, it'd be this amino group supplies all the electrons for the hydrogen, thus making the bond. Hydrogen bonds, need to know it. When a hydrogen atom forms a polar bond with another atom, it takes on a slightly positive charge. That slightly positive charge is attracted to a nearby negatively charged atom. Those are hydrogen bonds, and that's what water is so special because it can make a lot of hydrogen bonds. Individually, very weak, can be very strong when you have a lot of them, but need to know it's between 2 different molecules, and that's what this big line is. Not this erased one, but this big one is just showing you that it's the attraction between this positive over here and this negative over there. Water dissolves polar compounds because it's polar. Like dissolves like. So polar dissolves other polar things. Nonpolar dissolves other nonpolar things. So that's another word. So hydrophilic, soluble in water. Hydrophobic, not. Osmosis is the spontaneous movement of water across a semi-permeable membrane to an area of higher solute concentration. So this is pretty much just saying if you have, the body's trying to keep everything equal. So if you have a lot more, say, salt on this side, and not a lot less salt over here, the water is going to move across the membrane to try to dilute that high amount of salt. Just because it's too high and it wants to keep it balanced. So it's going to be, osmosis is the flow of water across a membrane. That's what you need to know. It's the flow of water. Trying to establish equilibrium. And it's driven by the differences in osmotic pressure from those other solutes. Isotonic solution, is when the osmolarity is the same. So iso meaning same. So there will be no net flow of water across the membrane because it's the same on both sides, right? Hypotonic solution, when the solution outside the cell is lower than the cytosol. So when that happens, water is going to, so there's pretty much more salt on the inside of the cell, for example, to continue it. So water is going to go into the cell to try to balance it out. Cell bursts. So the opposite happens with a hypertonic solution where the water flows out, cell shrinks. You need to know those. Our acids, need to know our acids, and I have them written out just in case. He writes it as that in the written out form, but if it says acid on it, it's probably going to be an acid. And for our bases, if it says hydroxide, that's just an OH, so that's going to be your base as well. So anything that says hydroxide on it, base.
Do we need to know just those, or do we need to know like all of them?
Probably just those.
Just these?
All right, pH. pH, need to know, it describes the hydrogen concentration of a solution, and that equation is pH equals negative log of hydrogen concentration. You know that equation. pH is on a scale of 0 to 14, 0 being the most acidic, 14 being the most basic. All acids are pH less than 7. All bases are pH greater than 7, so 7 is just our neutral. Need to know that human blood is 7.35 to 7.45.
Back to bases. Ammonium hydroxide is what?
NH4OH.
Okay, good.
Yeah. Buffers. This buffers resist large pH changes, and so when we add small amounts of strong acid or base, it can keep that pH hovering around where it needs to be. The definition of it is a weak acid and its conjugate base, or a weak base and its conjugate acid. You need to have sufficient amount of buffer for it to work. If there's not enough, it's not going to work. You know the Henderson-Hasselbalch equation. pH equals pKa plus log of A minus over HA, or the proton acceptor over the proton donor. I think at equal concentrations, know this too, at equal concentrations, the pH is equal to the pKa. Everything else just cancels out. Need to know the different examples of buffer systems, not how they work or anything, but just need to know proteins, hemoglobin, bicarb, phosphate. Just need to be able to pick which one is not one of those, if anything. Cool, carbon bonds, it can do a lot, what have you. Need to know our functional groups. If you don't know them by now, hopefully you figure out something for tomorrow. So methyl is just CH3, ethyl, 2 carbons, so C2, H5, what have you. Phenyl, we know phenyl equals circle. Our carbonyl group, we have 2 different carbonyl groups. We have our aldehydes, which is C double bond O to an H. We have our ketone, which is just our C double bond O in the middle of some kind of molecule. Our ether bond is just that oxygen connecting everything together. The bat that I drew, we'll get to it. It's a great picture. Our ester bond is our C double bond O with another oxygen attached to it with an R group going on. Contrast that against a carboxylate group, which is C double bond O. So it just ends right there. And when you ever see the suffix ate, you're thinking negative, right? So if we wanted to make carboxylate a carboxylic acid, we're just going to add that H onto that negative charged O right there. And that could be written out also as COOH. And then ester could be COOR. Acetyl group, I don't really have a good one for acetyl group. Just know that's C double bond O with a methyl attached to it. Our hydroxyl, we know our alcohols. And enol is just a carbon with a alcohol and another carbon attached to it. But it's a double bond right there. So if you see something like, if you see 2 If you see a carbon-carbon double bond, you're looking for an enol, because that's the only one that has a carbon-carbon double bond. Functional groups, need to know these. Amino does not have the oxygen. Amido does have the oxygen. Sulfhydryl, pretty self-explanatory. Sulfur, hydrogen. Disulfide, pretty self-explanatory. 2 sulfurs. Thioester, it's just replacing, it's like a regular ester, but it's replacing this oxygen with a sulfur. Thio means sulfur. Tertiary amine has 3 carbons attached to it in this functional group. Kind of ignore that one. So a secondary amine would have 2 carbons attached to it, and then this one would be like a hydrogen. A primary amine would have just 1 carbon attached to it. Phosphoryl, 1 phosphate with a bunch of oxygen surrounding it. Phosphoanhydride, 2 phosphates attached by an oxygen, which would kind of be considered, if you microscope into it, kind of an ether bond, kind of, but phosphoanhydride. There's examples. There's my beautiful bat. Chapter 1. Questions on chapter 1? Just trying to fly through it as much as possible. Amino acids, need to know that in humans we have the L isomers. And if you see 21 on the test, don't let that fool you. I don't know where the extra 1 comes from, but if you see 21 on the test, don't let that fool you. Yeah, actually on that. So if you do see 21 on the test, I think when we had it, it was 21 and 25. There was no 20. Go with the 21. But if it's 20 versus 21, you could say in the book it says 20. So that's what I would pick. But unless he told you something different in class. Chirality is everything attached to this alpha carbon is different, is all that means. So here's our basic amino acid structure. We have our alpha carbon, our hydrogen, our amino group, and our carboxyl group. And down here we have our R group. All those are different. Chirality. We have 1 amino acid that is achiral. Which is it? Glycine. Good. Stereoisomers is just the mirror images. So L has the OH on the left, D has the OH on the right. We have different amino acid classifications, which we will go over. Cool. Nonpolar aliphatic art groups. So we have glycine, achiral. How do we go from glycine to alanine? We methylate it, right? Good. Proline is special because no free R group, right? Valine, leucine, isoleucine are our branched chain amino acids. Methionine is special because sulfur doesn't make disulfide bonds. No. Cysteine makes disulfide bonds. Only cysteine. All right? You need to know that. Those are all our nonpolar aliphatics. So down here, glycine, no chiral center. It's got 2 hydrogens. All the other ones are chiral. You can methylate glycine to make alanine. Those are our branch chains. Good. Our aromatics, so these are the ones that were on our palms.
What is aliphatic?
It's just like just a straight line. I think so. I think that's what it means. I forgot. That's what my gut says. Phenylalanine, tyrosine, tryptophan, these are our aromatics, right? We know phenyl is a circle just in the name of it. So easy. Tyrosine has, all you got to do is add a hydroxyl group to phenylalanine and you have tyrosine. So those two go hand in hand. And then tryptophan, just remember that one. Polar uncharged, these are the ones. So we have serine, threonine, cysteine. So what's special about cysteine? Forms disulfide bonds, has sulfur. Serine, threonine, and tyrosine are, what do all 3 of those have? an alcohol group on it, a hydroxyl group on it. And what's special about asparagine and glutamine?
They contain an amino group.
Yeah, they have an amide group on them, so need to know those. You should be able to wrap those very quickly, or just read at the bottom of the page. All right, our positively charged R groups, right? This is Hal, our good buddy Hal. So histidine, arginine, lysine. That's how I remember those. And our negatively charged are aspartate, glutamate. They have AT in them, so there's a negative charge. Just make sure that if you ask you what the basic ones are, also say Hal. If you ask you which ones are acidic, aspartate and glutamate. You need to know those two also. So he could ask negatively charged, or he could ask which ones are acidic, and be able to, those are the same way he could ask a question. They're just different ways to ask the same question. All right, cysteine makes disulfide, not methionine. A zwitterion predominates at neutral pH. A zwitterion is can act as either an acid or a base. And I guess amphoteric is roughly the same thing, both acidic and basic. Haven't figured out what the difference is with that yet. Need to know those definitions. Need to know isoelectric point is when the net charge is 0. So up here, positive, no charge, negative. So this would be our isoelectric point where it's a negative charge, or when there's a neutral charge. Maybe just read over this just for your own information. See if that has anything to say. Here's kind of an example of titrating from that previous page. So we've got our buffer in solution. So we're titrating glycine, and we're in a basic solution. Or I guess we keep adding base. And it's buffer, so it's resisting change, and then we add too much. Boom, isoelectric point, PI, isoelectric point. And then we keep adding more, and then eventually it loses that last hydrogen, so it's positive, neutral, negative. Amino acids are formed with condensation types of reactions, making peptide bonds, link together different amino acids. You know that. It's between the amino and the carboxyl group. Okay, different types of modification. Need to know these. You can either add an OH, a COO minus, a CH3, an acetyl group, a phosphorus, or you can add carbs or fats to make different types of proteins. We'll get to proteins next chapter here in a second. Moiety just means like a part or piece. And just look over this real quick, modification of amino acids, just because it's the last page. Cool. Questions on chapter 2? Wonderful. Chapter 3. Yes. My guess. Who's got the answer? We're gonna do group. What? It's what? Positive?
Yeah. Well, the overall charge of an amino acid with a neutral R group be at any pH below the PI of the amino acid.
Cool. So. Someone toss me a pen. Good toss. Okay, so we got alpha carbon, hydrogen, carboxylate, amino, R group. Can you see that?
Yeah.
Cool. Net charge of this, 0, right? So there's no charge over here, so it's just positive, negative. They cancel each other out, okay? So when we go to this picture over here on page 22, if we can see that a pH, if we drop the pH on this left side, that's associated with this positive side. So it's going to be, that hydrogen's going to go back onto it. So if we, what's going to happen is, if we drop that pH, we're going to put a hydrogen there, and that's going to get rid of that negative charge, so that we're left with just a positive charge. So if we drop the pH and make it, and we put this in an acid, acids are hydrogen donors, right? So those acids are going to donate that hydrogen, and they're going to put it on that carboxylate group, thus getting rid of that negative, leaving only this positive. Good. And vice versa for when you're in a basic solution. Cool. Chapter 3, structure function relationships of proteins. You need to know that the 3D structure of the protein and thus its function is determined by the primary amino acid sequence. Function determines structure. Proteins have that covalent backbone of peptide bonds. So that's going to be your primary structure. But everything after that, stabilizing the structure, is going to be non-covalent. And those are hydrogen bonds, ionic bonds, or hydrophobic interactions. Different types of fibrous. Need to know which ones are insoluble or fibrous. Collagen, keratin. Which ones are globular, myoglobin, hemoglobin. Just think like hair and nails are pretty straight, whereas hemoglobin, myoglobin, we've all kind of seen the structure like this, pretty globular. Integral membrane proteins are proteins that are within the cell membrane, supporting with the structure. And this is an example of a membrane protein. If you ask you about channel proteins, they allow things to come in and out, but they're also integral. Amino acids, that we already talked about this, are condensation type reactions making peptide bonds. So if we're condensating out water, are we putting it in or losing it? Losing it, right? So we can always just hydrate it back, and we can put that water back in, break the bond, if need be.
And that would be hydrolysis?
Yes, yeah. Most peptide bonds have a transformation. It's just stabler, easier. Not stabler like SVU stabler, but like, really? Not one laugh about an SVU joke? Come on. They have a trans configuration, except proline, which has a cis, because it does have a free R group, messes everything up. Trans just means across or through, so that's kind of how the bonds look versus cis. These both go in the same direction. Not that big of a deal though. Protein structure, we got 4 different ones. Primary is just our amino acid sequence, so methionine, cysteine, valine, whatever, just that order. That's determined by the covalent backbone, the peptides, and disulfide linkages. So anything covalent, primary. Secondary is takes into regard the side chains. And this is hydrogen bonds. So secondary structure, hydrogen bonds, makes alpha helices, beta pleated sheets. I need to know that the alpha helix, the right alpha helix is more thermodynamically stable. For the beta pleated sheets, the anti-parallel beta sheet is more stable than the parallel ones, and that's just because of the hydrogen bonds. They can make more of them. They're stronger. Proline and glycine help make those the weird ones, right? The ones that are different from all the other ones. Not to single them out or anything, but I'm sure they're nice people. Tertiary structure. That's the overall 3D structure of an entire polypeptide, and that's motifs. So alpha helices and beta sheets that make patterns, making motifs. Quaternary structure is when you get multiple polypeptides coming together, making the protein. So hemoglobin would be something that has multiple polypeptides making a quaternary structure. You need to know what a native protein is. Native protein is the functional unfolded conformation of a protein. It's active, ready to go. Non-polar residues occupy the core. Polar residues are on the outside, so they can interact with water. It's hydrophilic. It likes water. And when you lose that native structure, it's denaturation. All right, so when we lose our structure, we lose our function, always. It's like if the structural integrity of our spine is compromised, right? So we're going to lose a lot of the function of our spine, right? It's going to degenerate, but chiropractic care can help with that. So there are some things that can cause denaturation, such as heat, changes in pH, detergents, ureas, alcohols, weak acids or weak bases. Those things can cause protein denaturation. But if we remove this, we can get back to our functional form. It's like subluxation, right? If you have a subluxation, you lose your function. But if you adjust that subluxation, take away the neurological the neurological block, put it back together, nervous system works properly, just like that. That's protein denaturation, renaturation. Spontaneous, innate intelligence, it's beautiful. But sometimes we get extremes, so like extremes of heat, strong acids or bases, extreme pH changes, when they can permanently destroy the native conformation. So in regular denaturation, renaturation, we're just losing like the hydrogen bonds or the non-covalent interactions. So we can just easily get those back. But when we break a covalent bond, that's not good. Those are difficult, if at all possible, to put those back together. So when we break those covalent bonds, we get permanent destruction. Here's a cute little picture of that. Next. Hemoglobin, myoglobin, need to know these charts. Myoglobin monomer, hemoglobin tetramer, so there's only one polypeptide chain in myoglobin. There's 4 in hemoglobin. Myoglobin, myo meaning muscle, present in muscle. Hemoglobin, present in red blood cells. Myoglobin, oxygen storage. Hemoglobin, oxygen transport. It takes it to our tissues and gets rid of it. It's like the delivery person. Oxygen combined, a heme prosthetic group. Whatever. Oxidized myoglobin is called met myoglobin. Need to know that word. Met myoglobin cannot bind oxygen, and that's because of this change to iron. That change in iron is where the oxygen binds, and when you change that iron, oxygen can't bind to it anymore. Myoglobin, oxygen storage. Here's a chart showing the different oxygen binding associated hemoglobin, myoglobin. Myoglobin has this hyperbolic curve, whereas hemoglobin has this sigmoidal curve, looks like an S. Myoglobin has a higher affinity for oxygen because it's storage, holds on to it tighter. Hemoglobin has a lower affinity, so it can get rid of it easier. Oxygen hemoglobin binding is allosteric and sigmoidal. It signifies the cooperative binding, which will go over here at the bottom of the page. Cool. Myoglobin, hemoglobin, like we said, myoglobin 1 chain, hemoglobin 4 chains. Since it's only got 1 chain, it can only bind 1 oxygen molecule. It's got a higher affinity and hyperbolic. Hemoglobin 4 chains, combine 4 molecules of oxygen, lower affinity so it can dump it to the tissues when it needs it, and sigmoidal change. Cooperative bonding, T is tense, R is relaxed. T is a 10 state. So what happens is once that first one binds, it's more likely that all the other ones will bind. It's a lot easier for the other ones to bind. Like gets the ball rolling per se. And then relaxed state, so it gets fully here, and then once it loses this first one, it's more likely to lose the rest of them. Oxygen binding to hemoglobin is allosteric, so we've seen that twice now. May be important. And cool. Curves, need to know the graphs. Need to know the graphs. The only one that's different is pH. pH is the opposite of all the other ones. This shows up on boards, so if you can understand these now, it'll be a lot easier for you. So when we cause a right shift will be an increase in CO2 temperature, or 2,3 BPG, and a decrease in pH, whereas a left shift is the exact opposite, where it's a decrease in those three and an increase in pH. Question?
Left shift is loading, right? And right shift is unloading? Right shift, the hemoglobin unloads quicker.
Yeah.
But that's in the tissues.
Yeah, so in the tissues, so I like to read it going this way. It's just easier for me. So when we have, this is our percent saturation on the left. So this is determined by our oxygen, our percent oxygen in the body. So as we lower our percent oxygen, once it loses that first one, it loses the rest of them. Yeah, so it'll dump it. A right shift will cause it to dump earlier, whereas a left will cause it to hold on longer. All right, so if we increase, this makes sense. So if we're working out, we're increasing our body temperature. And this is like a byproduct of glycolysis, what have you. And so because we have that increase in temperature from our body, the innate intelligence is telling us, hey, increase in temperature, we need to unload faster. So yes, unload quicker. We need that oxygen to be able to keep working out and sustain that level of performance. Cool. Normal form of adult hemoglobin is 2 alpha and 2 beta subunits, and that's HbA. We just went over this in clinical nutrition. Yes, not yesterday because that was Sunday. Last week, so shows up later. Fetal hemoglobin is alpha 2 gamma 2. So it keeps the alpha, switches the beta for gamma, has a higher affinity for oxygen. Sickle cell is alpha 2, beta sickle 2. It's the change of glutamate to valine there, and it causes a low affinity for oxygen. Questions on chapter 3? Enzymes, it's great. I think we stop at the beginning of page 60, at the end of page 59 for this, test 2 for y'all's purposes. That might change for other classes. Cool. Enzymes are biological catalysts. They're very specific. Everything in our body is very specific. And how they work is they increase the rate of reactions by decreasing activation energy or lowering the free energy of equations. But what's awesome is that the native nature of the enzyme remains unchanged before and after, so we can keep reusing them, which is really nice. Don't have to keep making them and wasting all that time. Cofactors, coenzymes, need to know the difference, need to know examples. So cofactors are our metals on the periodic table. Coenzymes are our vitamins. That'll be on the next page. Need to know the difference between holoenzyme versus apoenzyme. So a holoenzyme it's active, and that's equal to the apoenzyme plus its coenzyme or cofactor, whereas the apoenzyme is not active because it's lacking that coenzyme or cofactor. The coenzyme cofactor is like the battery that makes whatever you're using work.
For the cofactors again, and coenzyme, or is he just going to give us a list and say identify which the following is
if anything, I think if he would pair that on test 2 or 3, I think for this one he wants you to know if it's a cofactor or coenzyme. When in doubt, guess magnesium. It's the most common. I was actually talking with a lady yesterday about chiropractic, and I was watching the Super Bowl, and she was like walked in, and I was like, okay, what's up? And so we were like watching, not like in my room or anything, like in my like apartment. She didn't just like walk into my apartment. We were like in like the media room of our unit of our building, and I was talking to her, and she was like, yeah, you know, my doc. I told him that I wanted to like do a lot of holistic stuff, and so I've done a lot of research, and so I'm on like magnesium supplements, and I was like, yeah, that's like brilliant because magnesium is so used throughout the body. So whatever you're doing, whatever research you're doing, like or your holistic doctor is doing, like keep that up. And then she was with her family too, and I was like, y'all need to listen to her. She was like 75 years old, and they were all looking at her like with this like weird eye. I said, no, y'all need to freaking listen to her because she's brilliant. Anyway, prosthetic group. It's just anything that's not an amino acid that can bind to an enzyme. It's like a fat or a carb, what have you. We'll go over this here in a minute. You need to know row 3 or column 3, yes? Or that's what he said?
Is he going to give us like another type of vitamin that's not on there, or is he going
Probably
to
not.
Like so he's going to say like he's going to put copper, folate, riboflavin, and magnesium. He's going to say which ones are cofactors.
Potentially, yeah.
Okay, so it's not.
He might do that. He might say which one of these is a coenzyme, and then he might have ones that aren't, and you'd have to pick out the one that is.
Mm-hmm.
That's it, yeah.
Yeah, it could be either pick which one it is or pick which one it isn't.
So you could have like vitamin B3. I don't even know if that's a vitamin. Just saying, and that wouldn't be on there.
That would not be on there.
So that would be an example of a trick thing that he could do. Or no?
I don't think that's one of the questions that he's going to really try to trick you on,
Okay.
in my
I'm
opinion.
wondering how well, because if you know it has basically.
If it's a vitamin, I mean, over here it says all vitamins. So if you see anything that says vitamin on it, it's probably a coenzyme. Cool.
Yeah, I mean, I feel like that's what
Cofactors, metals, on the periodic table. Enzyme, just for your own benefit for now and for later. First part talks about the substrates, so what's acting on. Second part is going to describe the type of reaction, and these are the different types of reactions. I went over that a lot. Let's just go over it now. I'll go over it again. We're on page 118. Phospho, hexose, isomerase. So we said the first part of the enzyme talks about the substrate. So that would be this first word. So phosphohexose. Glucose is a 6-carbon sugar. So that's where the hexose comes from. Hexose just means 6-carbon sugar. And phospho means phosphate, right? So this is a 6-carbon sugar with a phosphate on it. This phosphate happens to be on the 6th carbon. Doesn't describe like that specifically, but generally that's what it describes. And then we're going to isomerase here. So isomer meaning what? Like the same or similar, right? So glucose and fructose are actually isomers of each other. And we can see that somewhere. Here we go. So they're isomers of each other on page 99. So glucose versus fructose. It has the same chemical formula. It has the same number of carbons, oxygens, hydrogens. They're just rearranged differently. So that enzyme, phosphohexose isomerase, is just talking about, hey, we've got a 6-carbon sugar, phosphohexose, and I got an enzyme that's going to make an isomer of it, making fructose 6-phosphate. Tells you all the answers you need.
If it said phosphopentose isomerase, it'd be like glucose 5-phosphate.
No, because glucose is a 6-carbon sugar.
Well, I mean,
It would be
yeah, but
it would be probably a ribose to a ribulose in that situation.
okay.
but we'll get there. That's just laying the foundation for later. Different types of reactions. Need to know the numbers. Need to know the name. You know what they do. So know that chart. Oxidoreductase are redox reactions. So that's either taking away a hydrogen or the transfer of hydrogens or of electrons. Could be hydrides as well, but generally it's hydrogens or electrons. If you ever see anything with the word dehydrogenase on it, it's an oxidoreductase, class 1. In this equation, we've got ethanol as our substrate. We have NAD, which is a coenzyme coming in, and it's stripping ethanol of hydrogens, leaving us with acetaldehyde. So that would mean that the NAD is our oxidizing agent, and our ethanol was oxidized, NAD was reduced, so ethanol was our reducing agent. Transferases, it's just the transfer of one group to another. So with this example, we have hexokinase, first enzyme of glycolysis, works on glucose, so we're transferring a phosphate from adenosine triphosphate, kind of written out terribly over here, with 3 phosphates over here, transferring one of those phosphates onto glucose, making glucose 6-phosphate. So here we just had an OH. Here now we have the phosphate group. Transfer, just talking about the transfer of one thing to another thing. Hydrolase, breaking a bond using water. There's a picture of a bond being broken by water. Lyase is the breaking of bonds using anything but water. So this would be fumarate malate. This is in our Krebs cycle. We'll learn that enzyme here shortly. Isomerase, we already talked about isomerase, previous example, but here's another one, triose phosphate isomerase. So triose, tri meaning 3. So this dihydroxyacetone phosphate has 3 carbons. So triose phosphate, it has a phosphate group on it. So it talks about that. We're going to make an isomer of it. So we're going over here, and we've got 3 carbons again, 1, 2, 3, with a phosphate on it, glyceraldehyde 3-phosphate. It's an isomer, dihydroxyacetone phosphate. The answer's in the words that are right in front of you. Just, it'll make your life a lot easier. And ligases is the only one that's making bonds here. Number 6. Quick terminology, enzymes are biocatalysts. They make reactions in our body go faster. Substrates, what binds to the enzyme, and our cofactor is what is required for that enzyme to work. Enzyme substrate binding due to non-covalent forces, so that we can not make permanent changes to the enzyme or permanently use up that substrate. So we need to know this lock and key order, right? Start with our substrates, end with our products. They're combined in the middle. While they're making those changes, they leave and part their separate ways. Right? You go on a date, you and your significant other, you're on the date, you did the date, you're driving her home, or him home, you go your separate ways. Cool. Or you're together, you kiss, you're at the end of the kiss, you completed it, you still go home because you're a good person. Function of enzymes is to increase your reaction rates. Your reaction equilibrium is not affected, right? So we can keep reusing those enzymes over and over and over and over again. Free energy, you need to know the definition of Gibbs free energy. It's the energy that a system has that can be converted to do work.
I think he said we didn't have to know free energy.
There whenever he came in after you.
He stopped here, so everything.
He said that we would do that next.
He did say we need to know transition states and stuff, but not Gibbs free energy.
Yeah.
Not page 55.
Well,
Cool.
Didn't he say we did have to know the transition states and stuff?
We'll get to transition states
Oh, it's the next
on this next page. It's just easier.
Page 60. We went over enzymes activity.
Yeah, we just
Cool.
say transition.
Cool, we'll do that. So enzymes increase reaction rate by decreasing activation energy. That's like the big picture. You need to know that if you don't. And here's a picture of that. So this is the amount of energy that it would take to get you from your starting point here to your end point there. So the example that I used earlier, I probably could have used that one last page, but whatever. So like you're trying to get from here to New York or here to Paris or wherever you want to go, or here to Austin. So you could either walk or drive and do that, and that's how much energy it would take, or you could buy your ticket. That's as much energy as it takes to get your ticket. Then, so you have your ticket now. You get on the plane, so that's your product, and then you get to wherever you need to go. So that's just, it takes a lot less energy to do those little things than it does to walk all the way to New York City, per se. So it lowers that energy requirement to get you to where you need to go. Enzyme kinematics. Need to know that Km is equal to 1/2 Vmax of the substrate. Add that last little substrate part in. That was on one of our tests. And I was like, ooh, it's like 1/2 Vmax, and then it was of the products or of the substrates, and it should be 1/2 Vmax of the substrate. You know this equation, delta G equals negative RT natural log of KEQ, equilibrium constant. What else? K1, just talking about this rate of the forward reaction. K2 is just reversing it. K3 is going from this enzyme substrate to the product. That one's irreversible. It's important because you want to keep your product. You don't want to like build a house and then tear it down and then have to do it over again. That sounds awful. You know the Michaelis-Menten equation. Vmax is on top. There is a plus sign on the bottom. You know that. Lineweaver-Burke, Vmax is associated with the y-axis. Pretty sure that's the only thing you need to know. I don't understand this graph, to be honest with you. But pretty sure that's what you need to know. You said y'all did go over this little part? Yes? So you need to pretty much just know those definitions then. So enzyme activity, I think I put this on y'all's mock. So enzyme activity is concentration of product formed per unit of time, whereas the specific activity enzyme is concentration of product per unit of time per concentration of the enzyme. So it's just a more specific definition. Cool. Any other questions? We flew through that. That was wonderful. Cool. Eat some lunch. Decompress. Palpate each other. If you're not palpating 5 people a day, you need to start. I'm telling you. Thank you all for being patient with me and the vodcast.